Now let's try to have a conceptual understanding about the concept of competing risks, especially any one single life if it is subjected to more than one decrement. For example, a normal life person, he can leave that state of normal either because of, let's say, retirement or because of death. Or a healthy state person, he can leave the healthy state either because of illness or because of death. So, wherever one single life is subjected to more than one decrement, wherein that particular life can leave the population because of more than one set of risks, we call that situation as a situation or all those decrements as a set of competing risks. Right? This is an example. And wherever we see competing risks, we generally resort to two kinds of mechanisms. One being the multiple state modeling. We use the mechanism where we use multiple state modeling, wherein the various concepts relating to Kolmogorov differential equations would be used for solving the probabilities part. And two, just like the life table approach for individual lives, we will look out as a multiple decrement table for this competing risk. So if I now let me focus more on this multi-state model itself. So here let's say I talk about a three-state model, very common application, right? Very common application. A person he is in an active state, he may move either to a retired state or to a death state. The same could be talked about with respect to sickness also. Instead of retired, I can bring in the sickness. The only difference being here, from an active state, he is going into a retired state. Let's say the transition intensity being sigma x. From an active state, he is going into a death state with a transition intensity mu x. And from a retired state, he is going into a death state with a transition intensity nu x. Here, there are no other moves because from death state, he can't go back to active or retired. From retired state, he can't go back into active. Whereas if I am looking at, instead of retired here, if I put sickness, then there is a possibility of one more line back here, because from sickness state, he can go back into the active state. So different kinds of states, depending on the states, this transition diagram that we are getting into could very much vary. So here I talk about these three as the states A, R, D, right? And anytime I talk about the typical transition intensity for an age x plus t, if I am talking about, let's say, AR, what does this mean? The transition intensity from state A to the state R at the time, by the time he reaches the age x plus t. That is what we are calling as the transition intensity. Which means if I am really supposed to compute TPX, let's say AR, it's as good as the probability that a person is in state R at time x plus t, given that he is in state A at time x. So this is what is the meaning of TPXAR, right? And here A and R are different states. So probability that a person is in state R at time x plus t or at age x plus t, given that he is an active person at the age of x. But the same thing if I write TPXAR with a dash over it, or probably AA. Okay, when I'm saying AA, okay, let me write it slightly again. When I'm saying TPXAA, it means that the probability that the person is active at time x plus t, given that he is active at time x. But nowhere there is mention about between x and x plus t. Probably in this example, no issues. He could have gone to retired, but he can't come back from the retired state to active. But imagine it's a sickness. So we are talking about probability that he is in state x plus t, state A at x plus t, given he is in state A at x. So because he can't come back here, this is same as the probability that he is in state A only from x to x plus 3, x plus t. You see the difference? When I just like write it like this, it means that the probability that he is in state A at age x plus t, given that he is in state A at age x. But when I write it as TPX AA bar, it means that the probability that he is in state A right from x to x plus t, given that he is in state A at x, means he did not change the state in the middle and came back to that state. That is not the case. He has been there forever in that state, which means if the return to this particular state A is impossible, once I leave this state, if I can't come back, in that case, I can very well say that TPXAA is same as TPXAA bar. For this kind of a model, I can very well say TPXAA is same as TPXAA bar, because once I leave the state A, there is no way I can come back to the state A. Right? But in some cases, probably if you look at this model, active, sickness, dead, ASD model. From active to sickness, I can come back from sickness to active. Let's say this is the transition matrix or transition intensities. Once I leave, so here TPXAA is not the same as TPXAA bar. The reason being, there is a possibility that he can go to S, stay there for a few months, come back by the end of the time x plus t age. But when we are talking about this, he has been there in the only state A, he did not move out from the state A. So when there is a possibility of return back to that state, once it leaves it, then these two cannot be equal. Otherwise, I can very well try to equate these two equations, but trying to understand what is the difference between this and this. And now to solve them, we know the Kolmogorov differential equations. Right? We have the Kolmogorov differential equations, dou by dou t. The forward equation that we have said, dou by dou t, if I want to get TPX from state G to state H, it is nothing but I am trying to TPX times TPX GJ times mu J H. So it is as good as I can take it as a matrix. So TPX times GJ multiplied by mu x plus tj, which means it is for j not equal to h. This is for j not equal to h, I am doing the summation, and it should not return back, which means from there I am saying TPX gh, it has already reached the state h, and from there it is returning back to some other state j. That probabilities we are taking out. So this would be the typical formula for dou by dou t of TPX GH. Whereas the GG, if I am looking at the TPX GG bar, we know that it is nothing but minus TPX GG bar times, I am doing it J not equal to G mu x plus T, mu x plus T GJ. And this would have resulted in a closed form solution e to the power of minus integrated between 0 to t mu x plus s ds. This is from G to J. So this would have given us a direct solution for TPX GG bar. And if at all we have some kind of a model like this, we can talk about computations of the present values of the death benefit for a person who is alive, or I can talk about a sickness benefit for a person who has been alive now. All kinds we can very well compute. So probably in the same, let's look at this model, the active, sickness, death. Right, let me compute some basic calculations on the top of this model. So from A to S, let me assume that the transition is sigma x. Here it is rho x. Here let's say the transition is mu x. Here the transition is nu x. Now I am talking about a lump sum benefit of 1 that is payable on death. Right, so either the death can come directly from an active state, or a person, he could have gone from active to sickness, and from there he could have gone to death. Okay, let's look at the overall probabilities for that. Let me assume that from active state he has gone to death, which means I am interested in finding out TPX, that he is in state active only until x plus t, and once he is active, from there he is gone to death, mu x plus t. Similarly, he has moved from state A to state S by the time he got x plus t, and from the state S he died. So from state S, if he has died, it is nu x plus t. Now this is the typical present value, because this is a probability and this is the intensity. So this is, so I will get this is the expected value, and I am finding out the present value of it, multiplying it by e to the power of minus delta t. So this is the present value. Integrate this over 0 to infinite, that will give me the expected present value of the death benefit. Similarly, when I am looking at the annuity in case of sickness, okay, what is the sickness part of it? TP, as long as he is in the illness state, as long as the person is in state sick from a time x to x plus 3, as long as, what is the probability that he is in state S, given that he is in state A initially, and I am paying a benefit of 1, and I want to find out the present value of it. So this is the present value, and I am integrating it over 0 to infinite. This will give me the expected present value of the same. And all these things can very well be simplified using the Kolmogorov's differential equations mechanism. So there could be closed form solutions when we are going with Kolmogorov differential equations mechanism. But this is where sometimes I can bring in, apart from the dependency on these Kolmogorov equations of this multi-state model, we can also talk about multiple decrement tables. In this context, we can bring out multiple decrement tables, wherein we'll introduce few new terms. AQX, probably here I'll say R, means retirement. What do I mean by this? It is the probability that the person whose age is currently X, right, he would be removed from this current state, whatever is the state that is there, between the time X and X plus 1 by this decrement called retirement, even if the other decrements are also present, means even if death is present, this is the probability that he will exit the population because of retirement. Whereas the same thing when I say QXR, it means it's independent. This is the dependent probability, and this I call as independent probability. So this is the probability that a person whose current age is X will move out of the population between age X and X plus 1 because of the decrement R, assuming that there are no other risks as a part of that particular population. Right? So this is what we are trying to understand when we look at the multi-decrement table, and a few important concepts that come into picture. Let's try to look at AQXD, D being the death. All we are saying is the probability that the person is in state active, he is leaving the population because of death. And now let me assume that retirement and death are the two models, two decrements that are there. I go with this ARD kind of a model. Right, let me look at the ARD model, where we are talking about from active to retirement sigma x, active to death mu x, retirement to death nu x. Right, now AQXDX is nothing but, given that the retirement is also there, the probability that the person will leave this particular state state X because of death. Now, if I am saying AQXD, I can very well, so the probability of a person whose age X is there, who is currently in an active state, within a year, via the decrement of death, is same as the probability of death in 1 year's time. So if I assume here, let's say this is not there, means this transition is 0. What is that I am saying now? AQX D. The probability that a person whose age X will leave the population because of death is same as the probability that a person who is currently in state active moves to the state death from age X to X plus 1. So these two mean one and the same. AQXD is same as PX A to D. This is one important relation, especially if no other transitions are operating. Right? If I assume that this is 0, this is an important relationship that is coming into picture. And now we can really try solving out AQX. Will, if at all in reality, we'll see AQXR as well as AQXD. How is that we are able to solve? Let's look at the differential equations from the Kolmogorov's part. We know that TPX from active state to the retired state, if I have to find out, it is from active, right? I have to go from active to active, multiplied by mu from active to retired. Active to retired is coming out to sigma x. Similarly, I am subtracting from again from there I can't go to retired in any form. And out of that I am also subtracting TPX. I am going from active to retired already, and from retired coming back to the death part. The only transition is the death, and which is coming out as nu x. So we know that the dou by dou t of TPX AR is same as TPX AA times sigma minus TPX AR times nu. And we know that TPX AR, right? If I want to know TPX AR, which is nothing but AQX, which is that AQXR, if at all the nu is going to be 0. So if nu is going to be 0, probably it's like the retired state is actually an absorbing state. So the probability of a life whose age is x leaving the state active through the decrement of retirement before the age x plus t is same as the probability that the same life is in the retired state at the age x plus t, because it is an absorbing kind of a state. So which means from here I could very well get T AQX R. So I can very well, in this case, I can very well write dou by dou t TAQXR. This part is not existing. So it comes out as TPXAA times sigma. And what is the TPXAA? We have already got it as e to the power of minus of summations of all the transition intensity. So towards the retirement it is sigma, and towards the death it is mu. So I can write it as e to the power of minus sigma plus mu times t. So this entire thing comes out as AQ of x. If I want, it comes out as sigma times e to the power of sigma plus mu into t. And the same kind of a solution I can get with respect to AQXD also. Similar kind of a solution if I want for TAQXD dou by dou t, I am getting a similar kind of a form, mu times e to the power of mu plus sigma times t. So if I can, now I got these two things, I can very well substitute t equal to 1, and from there I can typically solve these differential equations. AQXR becomes sigma by sigma plus mu times 1 minus of e to the power of mu plus sigma. Similarly, I'll get AQXD as mu by sigma plus mu times 1 minus e to the power of mu plus sigma. I can very well use these relationships to solve all these kinds. So I got how I compute in case of a transition matrices given. I could very well compute my AQX of R and AQX of D. Both of them I can compute based on the transition intensities through this mechanism. And so we have got the differential probabilities now. We have got AQX of R as well as AQX of D. And now we also know the QX, which are the independent probabilities, which is nothing but, if I am talking about QX of R, I am only talking about the moment that is coming from A. I'll take it as e to the power of minus sigma. Similarly, I am talking of QX of D, I'll call it e to the power of minus mu. Now that I have AQX, I have QX. right? So probably if I am looking at 1 minus of AQXR minus AQXD, we have already got the values, right? AQXR, we simply got it as mu by, sorry, sigma by mu plus sigma times 1 minus of e to the power of mu plus sigma. Similarly, AQXD, we got it as mu by mu plus sigma times 1 minus of e to the power of mu plus sigma. If I sum up these two things, it's directly coming out as 1 minus e to the power of mu plus sigma. So it becomes 1 minus of 1 minus e to the power of minus mu plus sigma, working out as e to the power of minus of mu plus sigma, right? And so overall it is working out as minus mu plus sigma is equal to logarithm of 1 minus AQXR minus AQXD. So mu plus sigma becomes the minus of this. So from here I can very well get, so mu plus sigma is coming out to this, and of course from here we can very well, mu plus sigma is coming out to this much, or from here it is working out as, okay, if I am taking it the other way, it becomes 1 minus of e to the power of minus mu plus sigma is equal to AQXR plus AQXD, right? AQXR, we have got it as sigma by this, AQXD is this much. So from here I can say AQXD is nothing but mu by mu plus sigma. I'll put it as minus log 1 minus AQXR minus AQXD. Mu by mu plus sigma into 1 minus of minus e to the power of minus mu plus sigma, which is nothing but this part. I'll get it as AQXR plus AQXD. So I am able to find AQXD in this particular form. So from here I'll get the value of mu. Mu comes out as AQXD times minus log 1 minus AQX R minus AQXD divided by AQXR plus AQXD. So this is what I am getting my mu as. But I know Qx of D is 1 minus e to the power of minus mu. So I do it as 1 minus of e to the power of that, and similarly Qx of R. So I'll get Qx of R as well as Qx of D. So which actually comes out as Qxd is 1 minus of 1 minus AQXR minus AQXD to the power of AQXD divided by AQXR plus AQXD. This is what will come out as QXD And if I'm talking of QXR, the only thing is here instead of D it becomes R. So this is the typical relationships that we can convert between QX independent probability because of the decrement, dependent probability because of the decrement, and any kind of numericals can be worked out accordingly. So because QX of R becomes 1 minus of AQXR minus AQXD to the power AQXD R divided by AQXR plus AQXD. So this will be the kind of relationship expressions that are there in a multi-decrement table. Once I have the dependent probabilities, I can link them with the independent probabilities and vice versa through these different kinds of relationships. And the comfort on the usage of all these different relationships is very much important to solve the numericals that are existing with the multiple state or multi-decrement kind of tables, right?